Hi, it's time for another math easy solution. Time to discuss further into the applied project, which is faster going up or coming down video series, and now look at question 5. And I'm not going to recap too much on this project, but I will go over a brief overview of this project and each question. Basically, the idea of this applied project was that was to ask the question: does it take longer to reach its maximum height for a ball? If you throw a ball in the air, directly in the air, does it take longer to reach its maximum height or to fall back to Earth from its maximum height? And in question 1, I went over my earlier videos. I'll just erase this. Yeah, question 1 went over basically the governing differential equation for the motion of the ball as you throw it in the air, and then derived the velocity function as a function of time. And then question 2 developed the height function as a function of time as well as you throw the ball in the air. And then question 3 looked at T1, which was the time it reaches, time for the ball to reach its maximum height, and it was this formula. And then for a specific case, determined that it was 1.86 seconds approximately for a ball of 1 kilogram, velocity 20 meters per second, etc. And then question 4 determined time T2, which is the time that it takes for the ball from its maximum height to reach the ground, and it was determined it was about 1.98 seconds. It's for the same ball in question 3, and thus it was determined that for that case, going up is faster. But that was a specific case. And now we're going to look at is question 5 is in general. Yeah, in general, to see if it's going up faster or slower. And not just a specific case of a ball weighs 1 kilogram, initial velocity, etc., etc., etc. Now we're just looking at a general case. So question 5 states, in general, it's not easy to find T2, which is a time from the maximum height to the ground, because it's impossible to solve the equation y of t equals to 0, where again, that's the height formula over here. So it's a really complicated equation, so it's hard to solve this when you make it equal to 0 and solve for t. It's actually impossible to solve it explicitly, but we can, however, use an indirect method to determine whether ascent or descent is faster. And again, solving this equation, I approximated this equation in question 4. So basically in question 4 we used the graph of the height function y of t. Because as you know, when the ball reaches the ground, the height is 0. So that's one way of solving it, but we can't solve it explicitly. So another way is we can use an indirect method to determine whether ascent or descent is faster. And the way to do that is we can determine whether y of 2 times t1 is positive or negative or 0, and I'll explain that in a bit once I read through the question. And it says here, show that y of 2 times t1 equals to this, m squared over p squared times g times x minus 1 over x minus 2 times ln x, where x is equal to e to the power p t1 over m. It's a complicated formula there, or just a bit tedious, but I'll go over all this and it'll make more sense as I get through this video. So then show that x is greater than 1 and the function f of x equals x minus 1 over x minus 2 ln x. That's just this function right here. This is just our f of x. Because these are just constants, so that's why it's written like that. So show that it's increasing for x is greater than 1. Then use this result to decide whether y of 2 times t1 is positive or negative, and this is what you conclude is ascent or descent faster. So let's go ahead and look at the solution here. But first of all, recall what I'm going to go over is why we're looking for this y of 2 t1. So and then trying to find out if it's positive or negative or 0 in this case. So let's look at the applied project, which was you were throwing a ball in the air. So let's say we throw it in the air, and then we have it, let's say, reaches its maximum height and then comes back down. And then so the height function y of t is like this. This is our Yeah, I'll just move that down there. So this is our y of t, and then the time it takes to reach its maximum height here, we'll call this, I'll just call this h max, or y max. I just want to use that h. So that's at this very top height, and the time it takes to reach it is t1, and then time it comes back down to the ground is t2. Yeah, and also recall from my earlier video that the graph of this function y of t looks something like this. So if we were to graph this out, I'll just graph it aligned with this. So this is t, this is y, like that, y of t. Yeah, so recall from question 4 that the graph looked something like this. So it would go, say the height would go like that. It's just a curve like that. So that is and this is the maximum height up top here. So that's the maximum height of the balls you throw in the air. This is the time, and then the time it takes to reach its maximum height here. This is our T1. And I'll write this T1 like that. And then the time it takes for the top of the ball to reach the bottom, or from the top to the bottom, is from here to here. And this is our T2. Yeah, now in this case we don't know if T1 is less than T2 or greater than, but the idea of looking at whether this is positive or negative, well, or 0. Yeah, or 0, well, let's look at those cases, what it means. So if you have y of 2 times T1, let's assume that it's shorter. So let's say that T1 is less than T2. So we have something that I'll draw in red. So this T2, this T1 is less than T2, like that. Yeah, I just drew this line a bit better. So there's T1 is less than T2, like that. So what this means, because as you can see, this is the case. So if T1 is less than T2, we have this case where, again, it's clearly less than it. So at this very point right here, that is y of 2t1, well, it's positive. As you can see, it's greater than 0. So that's this height over here as well. So that's the same thing as over there. Yeah, so the ball is still in the air if the time t1 is less than t2. But if we have the case where, let's say it's equal to it, so if it's equal to it, so this is t1 is equal to t2, and then this point is, well, pretty much at 0. Y of 2 t1 equals to 0 in this case. And then the final one, but first I just move this over there. I guess we're going to have to draw it out. So if t1 is greater than t2, and again from that question 4, this equation actually keeps going on, this graph keeps going on for, let's say, negative height if you were to just draw it fully out. So this means that if you had, because of the function the way it is, it looks something like this. So if you had t1 greater than t2, then what we'll have right here is this maximum height, this height at this point right here, y of 2 t1 is less than 0. So you'll have a negative height if it's longer than it. Yeah, which makes sense, because if it takes longer for it to reach its maximum height, and then if you will, y of 2 times that time, that's obviously going to be, the ball's already hit the ground way before it. So that's the indirect method we're going to look at. And again, this y2 of t, that's at this point. In other words, that's just this height across all the way here. So that is the same thing as like that. So, yeah, so let's go ahead and start solving for this y of 2 t1, and then decide if it's positive or negative. So the first part of the question is, show that y of 2 t1 is equal to all this. So what we'll do is first, again, recall that t1, the formula for t1, let's go all the way up to earlier. So that's just from question 3. So m over p, where m is the mass, p is the coefficient of air resistance, times ln of mg plus pvo, where vo is the initial velocity of the ball, g is acceleration due to gravity, then all divided by mg. Let's see if I remember that. So m over p times ln of, this is mg plus pvo over mg. Yeah, so that's what we have there. And also recall that, well, the y function, so y of t is equal to, well, again, let's scroll above. I think that was also from question, that's from question 2. So VO plus mg over p, m over p, 1 minus e negative pt over m minus mgt over p. Let's see if I can remember all that. Yeah, so that was, I think, VO plus mg over p, m over p, and then was 1 minus e negative pt over m, and then minus mgt over p. I just want to double check. So VO plus mg over p. Let's go back up. Yeah, VO plus mg over p. Yeah, so this is right. So this is what we have, and I just moved it over to the left just to be a bit neater. So that's what we have. So now let's look at what happens when you plug y of 2t1 inside. So these are all just constants. There's no t in these. So this is VO plus mg over p, m over p, m over p, and then now what we have is 1 minus e to the negative, and I'm not going to plug in the full value inside. We're going to have here 2p t1, because we have 2 times t1, and the reason I'm doing just like that on there, because we have that x formula we want to use to simplify it, and I'll simplify it in a bit. So we're x equals to e to the power t ep t1 over m minus mg over p. Yeah, mg over p, and then we have now, let's just plug in our t1. Actually, it's not enough room, so I'll move this over to here. So let's move it over here, times it by m over p. I mean, this is going to be 2 times m over p. So we'll put a 2 all the way in front, because there's 2 times t1. So 2, and then m over p ln m over p. Times it by ln of, and I'll put a bracket, a square bracket around, because we have another bracket in here. So it's just very tedious stuff, but then we'll have PVO over mg. So that is what we have. And now let's simplify this further by using that x equation. So let x equals to e to the, just because I don't want to plug in the t1 inside this power. So that was the idea of using the x formula. Yeah, so that's the idea of using it. So the x was equal to pt1 over m, and that's because I still want to plug in this giant formula inside here, and that's what the calculus book also recommends. So x equals e to the pt1 over m. And now if we were to plug this inside, the t1 inside there, we have e, put this down, p over m, and then we have this giant t1 formula inside. So we have a m over p, and then ln of mg plus pvo over mg, and then all bracket like that. So as you can see here, this cancels with this cancels with that, and we're left with e to the ln of mg plus pvo over mg. And recall the logarithmic properties, natural log properties in my earlier videos. You can see that in the video link below. E to the power of ln of anything, the e and ln cancels. We're just left with the numbers inside the ln function. So this means that x is equal to, and there's no other power here, these all just cancels as 1. X equals to mg plus pvo over mg, which is this value right here. That is this x. So we've simplified that as well. So that's x is equal to this right here, as well as pt1 over m. And then we have this negative 2 pt1 over m. And again, recall the power function properties. If you have, let's say, a to the power of negative, e to the power of negative b, for example, or negative 2b, this is the same thing as writing a to the power of b and then all to the power of negative 1. In this case we have a -2 there, so what we have is, and again you can see more on the power properties in my earlier videos as well in the video link below in the description. So we have this e to the -2 pt1 over m. Same thing as writing, well, e to the, and then take the negative, but there's a 2 as well, take the -2 as well, you could do. So we'll have here, this is going to be pt1 over m, power of -2. And the reason we're doing this is because, well, e to the power of pt1 over m is x. So this is equals to x power of -2. So that's another way of simplifying it. Yeah, now before going further, I'm going to simplify this as well, this part right here. And the reason is because we can, it looks somewhat like this mg plus pvo over mg. So we'll make it look like that so that we can replace it with an x. So I'll go right here, or I'll write note just to indicate that we're going to be solving this. So VO plus mg over p, well, what this equals to is, well, let's multiply by both sides on p on this side. So we'll have a p over p. This adds up, we'll get a p VO plus mg over p. Yeah, over p like that. And then to make it look like this, well, all we need to do is have an mg at the bottom. And also flip these around. So what I'll multiply this is by mg top and bottom. And then we'll just flip this p out and move these around and make it look like the x1 a bit neater. So we'll have a mg plus pvo, all we're doing is switching those, no difference. And then put the mg inside. And then now what we have is, and take the p out, it's the same thing, we're not changing anything. So mg over p. Where this equals to, well, that's just our x value. That's just our mg plus pvo over mg. So we have x times, yeah, we'll have x times mg over p. So that is what that part equals to. So let's put these all together. So we've got a bunch of simplifications, and put these all together, we get, we get y of 2t1 is equal to, so the first bracket was this, that's our x times mg over p. So we have x times mg over p, and then what we have here is an m over p, times it by m over p. I don't know why this is so far out, make it a bit neater, times it by m over p, and then finally we have 1 minus e to the -2 pt1 over m, that's just x power of -2. And then what we have now is minus, and then what we're minusing here is this 2mg, these add up, so m squared p squared, and then the g is left alone, then we have a ln, and then that's just x. So we have 2 times m squared p squared g ln x. So that is what we have, times by ln x. So now we just simplify this further. So this m's will have m squared p squared, so this equals 2, and then I'll put this out, m squared over p squared g, and put the x on this side like that, and then times it by 1 minus 1 over x squared. Simplify that like that, write it neater. And then again 2m squared over p squared g ln x. And now we have a common denominator, and also I'm going to multiply these inside. So what we have is right here, this m squared over p squared times g that occurs here, those are just constants, so we could take those all out. So p squared g, and then we have this, we're going to multiply this inside, so that we'll have x times it by, and then that's just x times 1 is x, x times 1 over x squared is just, well, 1 over x. And then, because we took the denominator out, now the common factor of m squared p squared g squared out, all we're left with is 2 times ln x. So there it is. yeah, I'll just put a better bracket. So there is our y of 2t1, and this is exactly what we were asked to solve. Y of 2t1. I'll do that, and let's just double check. So scrolling up, we were asked to solve m squared over p squared g, and then x 1 over x minus ln x, and that's what our f of x function is. And now we're asked to solve is show that x is greater than 1, where x is this, and the function f of x equals to x minus 1 over x minus 2 ln x is increasing for x is greater than 1. So let's look at x is greater than 1 first, show that. Again, that's what our x is. So I'll just write part 2. Or I'll just ignore that, I'll just write, okay, so we have to find that x is greater than 1, so x is equal to e to the pt1 over m. And now what we have to do is, well, recall that p is greater than 0. It was a positive function for the air resistance, and you can see that in our question 1 video. Here, p is a positive constant. And again, you could recap on that. So it's a positive constant, is greater than 0, and also t1 is greater than 0. We're not going to have a negative time, and the mass is greater than 0. We're not going to have a negative mass. So all these are greater than 0. This means that, so what this means is that pt1 over m is greater than 0. Everything's positive. So what we have here now, and again, you can't have a 0 mass, you can't have a 0 air resistance, and 0 time doesn't make sense either. You're not teleporting to the top of the height, of the maximum height. So what do we have here? E to the pt1. So this means that this x value is greater than e to the 0, because these are all greater than 0. And recall that e to the 0 is just equal to 1. So this means that, well, x is greater than 1. Because e to the 0 is 1, and this is greater than e to the 0. So it's x is greater than 1. Alright, so now what we have to do is that we show that x is greater than 1. It says show that f of x is increasing for x is greater than 1. Okay, let's just do that now. So, so recall that, well, our f of x is equal to, let's just scroll up what it was. This is our f of x actually, which is x minus 1 over x minus 2 ln x. And just to double check, so that is exactly it. So this is the bracket inside here is our f of x. So to find out if it's increasing, well, this is x minus 1 over x times minus 2 ln x, like that. So to find out if it's increasing, we look at the derivative or the rate change of this function. Again, you can see more on this in my earlier video on the increasing decreasing test videos a while back in the video links below. So what we have, the derivative f prime of x is equal to derivative of x is just 1, and minus right here the derivative of this. This is the same thing as writing, I'll just write d over dx. I just don't know it on top of my head. The same thing as writing x to the power of negative 1, so we'll take the derivative of it afterwards. So 2, and then this is x. So derivative of ln x is just 1 over x. So we have 2 over x like that. And I wrote this like that because it's easier to take the derivative of it. So 1 minus, and then this goes down. So we'll have a negative 1. And then x, take a power out, negative 2, like that, minus 2 over x. And this is the same thing as writing 1, these become positive, this is, well, 1 over x squared. I just flip that down, minus 2 over x. So that's what the derivative equals to. And what I'm going to do is simplify this further by using common denominator of x squared. So multiply top and bottom by x squared, so we're not changing anything. So multiply this x squared inside. What we end up getting is, well, there's an x squared, and then this x squared just cancels, it's just plus 1, and then this negative 2x, one of the x's cancel, so we're left with minus 2x over x squared. And I'll just simplify this a bit further. I just want to rewrite this, put the x in front, 2x plus 1 over x squared. And now what this looks like as well, what we could do is actually, you notice that this is a square on the top. In other words, recall that if we had something like x minus 1, if we had x minus 1 squared, this just equals 2, because we have this x squared minus 2x plus 1. This is the same thing as writing x minus 1 times x minus 1, and then multiply this by this. This is x squared, and then add it by this x times negative 1, that's negative x. Same thing here, negative x, and then here plus 1, negative 1 times 1. This is plus 1. This equals 2x squared minus 2x plus 1. So that's what this top part equals to. So in other words, the derivative, so now we have the derivative f prime of x is equal to, and then this is going to be, well, x minus 1 squared over x squared. Yeah, and as you can see here, whatever number you put inside here, especially if you put x is greater than 1, you'll have, well, just greater than 0. So this derivative is greater than 0 for x is greater than 1. Yeah, because if you put a 1 inside, then you'll have a 0. So it is for x is greater than 1. This is greater than 0, and it's not in any way equal to 0 either. So that is what we've proven now. And because derivative is greater than 0, this means that f of x is increasing. Yeah, increasing for x is greater than 1. So derivative of greater than 0 is the same thing as saying it's increasing. That f of x is increasing. So let's go up to the next part of the question. So it's saying use this result to decide whether y of 2t1 is positive or negative, and then this is what do you conclude? Is ascent or descent faster? So let's look at this. So it's saying that this f of x is always increasing. Yeah, it's always increasing. So let's look at our y of 2t function. So y of 2t1 is equal to, let's scroll up again. So that's m squared over p squared times g, and then that's our f of x. So we have a m squared over p squared times g, and then times it by our f of x, where this is f of x is just equal to, again, I just want to clarify again, so this x minus 1 over x minus 2 ln x is our f of x, and again that's from here as well, and it's just a function of x. So that's what it is right here. So this is greater than 0, because these are all just positive constants. That's acceleration of gravity, and these are squared anyway. So that's greater than 0. Let's put like this. This is greater than 0. And also here, this is increasing. So it's increasing, but let's see, yeah, it's increasing for x is greater than 1, and x is greater than 1 for all cases. Yeah, so also note, so it's increasing for x is greater than 1, and now we want to know if it's ever negative. Well, let's put a note here. Note, if x equals to 1, which it isn't anyways, it's always greater than 1. So if it is equal to 1, we can easily see that f of x, or f of 1, is equal to, well, let's look at our function again. Our f of x function is x minus 1 over x minus 2 ln x. Just plug that in. So so 1 minus 1 over 1 minus 2 ln 1. So 1 minus 1 is 0. And this is a 2 ln 1. And also recall, I'll put a bracket to make it look a bit clear. And also recall that, again, the ln properties, what these all mean is that ln 1, let's say it equals to z, not y, because we're already using y. So ln 1 equals z is the same thing as writing e to the power of z is equal to 1, or just ln, or e to the power of both sides. And the only way this is true is if z is equal to 0. So we have e to the 0 is equal to 1. So this equals to 0. So 0 minus 2 ln 1 is just 0 minus 0, which equals to 0. So if x equals to 1, f of 1 is equal to 0. and that x is and then x is always greater than 1 because we've already shown that. Yeah, we already showed that x, which equals to e to the pt1, is always greater over m is always greater than 1. So this means that even if x is 1, you have 0, and then it's always increasing. So it's always increasing. It's always going to be positive. So this is greater than 0. So if it's greater than 0, so thus, since, we'll write this, since y of 2t1 is greater than 0, and again, recall from my very first graph of this video, as you can see, the whole idea was to see if y of 2t is positive or negative. So this means that this is positive. In other words, it's here. So t1 has to be less than t2 because it's positive. So the ball's still in the air. So y of 2t1 is greater than 0. So, yeah, so since y of 2t1 is greater than 0, then t1 has to be less than t2. In other words, yeah, let's put an exclamation point. In other words, ascent, which is the time it takes to reach the top, which is t1, versus descent, which is the time it takes for the ball to reach the ground from the height, is t2. So ascent, yeah, so thus ascent is faster than descent. So there is our answer. I'll just circle all this. So thus ascent is faster than descent, which is quite remarkable actually. Because my initial prediction of this whole applied project was that it would be the same, because you're just throwing the ball, what goes up must come down. That didn't see any differences. Yeah, but one speculation on why ascent might be faster, I think, is because you're starting off from a super fast velocity initially when you throw it, so that I would assume there's just somehow more air resistance, like to build up quicker, as opposed to when it's falling from the top, you're gradually building up speed, so air resistance can, yeah, it's more uniform and thus slower. Yeah, I mean, it builds up more uniformly, so you'll have a bit more air resistance on it. Yeah, that's just what I'm speculating, but I'm not sure too much about that. And here, what I'll just paste, here's another important note that my calculus book has on this applied project. It states, in modeling force due to air resistance, various functions could have been used depending on the physical characteristics and speed of the ball. And this project used a linear model, which was just negative p times v, whereas p is the coefficient of air resistance, times it by velocity of the ball, and we're doing negative because it's always opposite of the direction or motion of the ball. Yeah, it's the direction of the ball. But a quadratic model is also another possibility for higher speed. So in other words, negative pv squared on the way up, or and then pv squared on the way down. So if it's really fast velocity, you're going to have, you would assume there's more air resistance to it. So this is another model, as you can square it. For a golf ball, experiments have shown that a good model is in fact negative PV times to the power of 1.3, yet going up, and then PV 1.3 was absolute value going down, because its air resistance would be going up when you're going down, because remember it's opposite of the motion of the ball. Yeah, but no matter which force function, negative f of v, because again it's opposite of the direction of the ball, and it's always related to the velocity. So if you use one that's related to velocity like this, so no matter which one is used, where this force is greater than 0 for velocity is greader than 0, and it's less than 0 for velocity is less than 0. Yeah, in other words, this is just the opposite direction. That's what I'm explaining. So regardless which one you use, the answer to the question remains the same. Yeah, and that is ascent is faster than descent. So in our case, we did linear model, but regardless of whichever one you use, it's always ascent is faster. So for a proof with a general air resistance formula F of V, please see the following paper by Brad Brower, What Goes Up Must Come Down Eventually. It's It's in the American Mathematical Monthly, volume 108, number 5, etc. This is in 2001 in May. Pages 437 to 440 of that journal. And here's a link to it. I'll also put the link in the video link below. But if you click it, you could also download it. And here's that proof article. I'm not sure if they go fully into proof, but they do go over. So here, what goes up must come down eventually. You could read it if you want. I haven't gone through it too much, but I know that they use a general formula for their resistance as opposed to our linear model, and regardless, they still come up with the same end result. And let's see if I can find that. Yeah, so the time that it takes to fall from maximum height is greater than the time to rise to maximum height for arbitrary retarding force of friction or air resistance. So any arbitrary one, it's a as explains here, it doesn't matter. It's always going to be faster ascent and slower descent, which is pretty remarkable. So yeah, if you want to go over further into this, make sure to check out this article or this journal paper as well. Anyways, that is all for today. Hopefully you learned from this pretty extensive question 5 video of this applied project. That's all for this applied project. Hopefully you paid attention or followed along. It's pretty extensive but very interesting mathematics and the application of mathematics for something so simple as throwing a ball in the air. So I would have just thrown a ball in the air. Who would have thought that reaching the maximum height is faster? I always thought it was going to be the exact same. I'm still not 100% sure why that is the case. So this was my initial prediction. Should be the same, but it turns out it's faster to ascend than descend. Anyways, that's all for today. If you learned, like always, you can download these exact notes in the link below. And thanks for watching, and stay tuned for another Math Easy solution.